The Bernoulli family, a lineage of brilliant mathematicians and physicists, left an enduring mark on science. From the late 17th to the 18th century, this Swiss family fostered intellectual curiosity, tackling complex mathematical problems. Their contributions spanned calculus, probability, fluid mechanics, and astronomy. Daniel Bernoulli, born in 1700, was destined to become one of the most celebrated members of his family. His work in fluid dynamics revolutionized our understanding of fluid behavior. Despite internal rivalries, the Bernoulli family's impact on mathematics and physics remains undeniable. Daniel Bernoulli was born in Groningen, Netherlands in 1700. His father, Johann Bernoulli, a renowned mathematician, shaped Daniel's early education. Despite Johann's aspirations for Daniel to pursue medicine, Daniel's true passion lay in mathematics and physics. Daniel enrolled in the University of Basel for a medical degree, but continued to study mathematics and physics in his spare time. Recognizing his son's talent, Johann eventually allowed Daniel to fully embrace his passion. This decision set Daniel on a path to groundbreaking discoveries. Daniel Bernoulli was captivated by the movement of fluids. He sought to express their behavior through mathematics, leading to his profound discovery, Bernoulli's principle. Bernoulli noticed that as the speed of a fluid increased, its pressure decreased, and vice versa. This inverse relationship formed the crux of Bernoulli's groundbreaking principle. Imagine a river flowing through a narrow gorge, speeding up and decreasing in pressure. This principle has profound implications for understanding phenomena like airplane lift and everyday devices. Bernoulli's insights into fluid dynamics were captured in a single, elegant equation. The equation represents a balance of energy within a flowing fluid. It includes terms for static pressure, kinetic energy, and potential energy. Bernoulli's equation encapsulates the principle of energy conservation within a fluid. As a fluid flows, any increase in one form of energy must be accompanied by a decrease in another. This principle provides a powerful tool for analyzing fluid behavior. Bernoulli's principle is key to understanding aviation. It explains how an airplane wing generates lift, counteracting gravity. The curved upper surface of an airfoil forces air to travel faster, creating lower pressure. The pressure difference between the upper and lower surfaces generates lift. Factors like airfoil shape, angle of attack, airflow speed, and air density affect lift. Engineers optimize these factors to achieve controlled flight. Bernoulli's principle influences many fields beyond aviation. In medicine, it helps understand blood flow and design devices like stents. Everyday devices like perfume atomizers and carburetors rely on Bernoulli's principle. Even a curved baseball pitch can be explained by pressure differences. Bernoulli's work demonstrates the enduring relevance of fundamental scientific principles. His principle continues to inspire awe and wonder in the interconnectedness of the physical world. Daniel Bernoulli's curiosity extended to the nature of gases. He envisioned gases as a chaotic dance of tiny particles, laying the groundwork for the kinetic theory of gases. This perspective challenged the prevailing views of gases as continuous substances. Bernoulli saw gases as collections of minuscule particles in constant motion. This concept explained gas properties like compressibility, pressure, and temperature. Bernoulli's vision provided a more accurate understanding of the gaseous state of matter. Bernoulli connected microscopic gas behavior to macroscopic properties. Gas pressure results from the constant bombardment of gas molecules against container walls. Faster-moving molecules collide more frequently, increasing pressure. Temperature is linked to the kinetic energy of gas molecules. Heat transfer occurs as faster molecules transfer energy to slower ones. Equilibrium is reached when the average kinetic energy of molecules becomes equal, resulting in the same temperature. Section 3, From Bernoulli to Boltzmann, a legacy of kinetic theory. Daniel Bernoulli's groundbreaking insights into the microscopic world of gases, though revolutionary for his time, were just the beginning of a scientific journey that would continue long after his lifetime. His work laid the foundation for the kinetic theory of gases, a field that would blossom in the following centuries, culminating in the elegant statistical mechanics developed by physicists like James Clerk Maxwell and Ludwig Boltzmann. Maxwell, building upon Bernoulli's foundation, incorporated the concept of a statistical distribution of molecular speeds into the kinetic theory. He recognized that gas molecules within a container do not all move at the same speed. Instead, their speeds follow a specific distribution, with some molecules moving faster and others slower than the average speed. This distribution, known as the Maxwell-Boltzmann distribution, provided a more nuanced and accurate description of gas behavior. Boltzmann further developed the statistical interpretation of kinetic theory, demonstrating that the macroscopic properties of a gas could be derived by averaging over the possible states of its countless constituent molecules. His work provided a rigorous mathematical framework for connecting the microscopic and macroscopic worlds, solidifying the foundations of statistical mechanics. Bernoulli's legacy in the realm of kinetic theory extends far beyond his specific contributions. His willingness to challenge the prevailing dogma of his time, to envision the invisible, and to connect the microscopic to the macroscopic, paved the way for a profound shift in our understanding of matter. His work serves as a testament to the power of imagination and intellectual curiosity in shaping our scientific worldview. Section 1. Embracing uncertainty. Bernoulli's foray into probability. While Daniel Bernoulli's work in fluid dynamics showcased his mastery, his intellect extended to the abstract world of probability. Bernoulli sought to bring order to chaos, developing tools to quantify risk and predict future events. He saw probability's relevance in finance, medicine, and weather prediction. Bernoulli's work laid the foundation for modern probability theory. Section 2. The St. Petersburg Paradox. Challenging the mathematics of expectation. Bernoulli's St. Petersburg Paradox challenged the traditional notion of expected value in probability theory. The paradox involves a coin-flipping game where winnings double with each consecutive flip. The expected value of the game is infinite, but no rational person would pay an infinite amount to play. This highlighted a flaw in the application of expected value. Bernoulli argued that the value of money is not linear. Section 3. Beyond expected value. The birth of utility theory. To resolve the St. Petersburg paradox, Daniel Bernoulli introduced utility theory. This theory revolutionized how economists approach risk, recognizing that utility is not linearly related to wealth. Bernoulli argued that the marginal utility of wealth diminishes as wealth increases. This principle explains why individuals are risk-averse and willing to pay for insurance. Utility theory has profoundly impacted economics, finance, and decision theory. It forms the basis of modern portfolio theory and behavioral economics. Bernoulli's exploration of vibrations. Daniel Bernoulli's curiosity extended beyond fluids and gases to the vibrations of strings. He explored how a plucked string's vibrations create melodies. Bernoulli applied mathematical rigor to understand sound production. He analyzed vibrating strings, revealing their harmonic frequencies. These harmonics add richness to the sound, defining each instrument's unique timbre. Section 2. Resonance. When systems sing in harmony. Bernoulli's exploration of vibrating strings led him to a profound and ubiquitous phenomenon known as resonance. Resonance occurs when a system is subjected to a periodic force at a frequency that matches or is close to its natural frequency, the frequency at which it naturally oscillates when disturbed. When this happens, the system absorbs energy from the external force, causing its amplitude of oscillation to increase dramatically. Imagine pushing a child on a swing. If you time your pushes to coincide with the natural frequency of the swing, each push adds a little more energy to the system, causing the child to swing higher and higher. This is resonance in action. The swing driven by a periodic force at its natural frequency, amplifies the energy input, resulting in a large amplitude oscillation. Bernoulli recognized that resonance was not limited to mechanical systems like swings or strings. He understood that it was a fundamental principle that applied to a wide range of physical systems, from acoustic resonators to electrical circuits. He observed that resonance could be both beneficial and destructive. In musical instruments, resonance is harnessed to amplify sound and create the rich, full tones we associate with music. The body of a guitar or violin acts as a resonant cavity, amplifying the vibrations of the strings and shaping the instrument's overall sound. In bridges and buildings, however, resonance can be a destructive force. If the wind or ground motion excites the natural frequency of a structure, the resulting vibrations can cause catastrophic damage, as seen in the infamous collapse of the Tacoma Narrows Bridge in 1940. Section 3, From Music to Machines: The Legacy of Vibrations and Resonance. Daniel Bernoulli's contributions to the understanding of vibrations and resonance have had a profound and lasting impact on science, engineering, and our everyday lives. His work laid the foundation for the field of acoustics, the science of sound, and contributed to our understanding of wave phenomena in general. In music, Bernoulli's insights into the nature of vibrating strings and resonance revolutionized the design and construction of musical instruments. His work led to the development of new and improved instruments, capable of producing a wider range of sounds and more expressive musicality. From the resonant chambers of concert halls to the intricate mechanisms of a piano, Bernoulli's legacy can be heard in the very fabric of music. Beyond music, the principles of vibrations and resonance play a crucial role in a wide range of technologies that shape our modern world. In telecommunications, radio and television signals are transmitted and received by exploiting the resonance of electrical circuits. Medical imaging techniques like magnetic resonance imaging, or MRI, utilize the resonance of atomic nuclei to produce detailed images of the inside of the human body. Engineers rely on Bernoulli's insights to design structures that can withstand the potentially destructive forces of resonance. Bridges and buildings are carefully designed to ensure that their natural frequencies do not coincide with the frequencies of expected environmental vibrations, such as wind or earthquakes. Damping systems are often incorporated into structures to dissipate energy and prevent the buildup of large amplitude oscillations. Daniel Bernoulli's exploration of the seemingly simple act of a vibrating string opened up a world of scientific inquiry, revealing fundamental principles that govern the behavior of systems ranging from the tiniest atoms to the largest structures. The Flow of Life: Bernoulli's insights into hemodynamics. Daniel Bernoulli's curiosity flowed between disciplines, illuminating the workings of the human body. His medical training provided a unique perspective on fluid dynamics and blood flow. Bernoulli's principles applied to blood circulation, revealing the heart as a pump. His work laid the groundwork for hemodynamics, influencing cardiovascular disease understanding. A legacy of flow: Bernoulli's enduring impact on medicine. Daniel Bernoulli's insights into blood pressure, flow rate, and vessel diameter revolutionized cardiovascular health. His principles guide medical education and practice, influencing diagnostics and treatments. Stents and Doppler ultrasound are just a few innovations inspired by his work. Bernoulli's legacy in medicine exemplifies the power of scientific inquiry. The enduring ripples of genius. Daniel Bernoulli's work stands as a towering achievement in science, a testament to human curiosity and natural laws. His contributions span fluid mechanics, probability theory, kinetic theory, acoustics, and medicine. Bernoulli's legacy is a testament to the interconnectedness of knowledge and human potential. Imagine a pebble dropped into a still pond. The ripples spread outward, their influence never truly disappearing. Bernoulli's work created ripples that continue to influence science and engineering. A timeless legacy: Bernoulli's gift to humanity. Daniel Bernoulli's contributions to science are not confined to academia. His insights shape our world and improve our lives. From airplanes to medical devices, Bernoulli's legacy is woven into modern society. His work on fluid dynamics aids aircraft design and other aerodynamic innovations. His principles optimize liquid flow in pipelines and irrigation. Even garden hoses benefit. In medicine, his insights revolutionized cardiovascular understanding, leading to better diagnostics and treatments. Bernoulli's work inspires curiosity and interdisciplinary thinking. His legacy continues to shape our world.